Good evening, good afternoon, good morning, good night, good whatever time of day it is that you've finally gotten around to watching the Chapter 8 video or going over the Chapter 8 slides and playing them. Chapter 8, of course, is of the alternative text, the ArcGIS Pro text, to Getting to Know ArcGIS Pro, by Michael Law and Amy Collins. And what I'm going to do is just do a quick overview of Chapter 8. This particular book doesn't go very deep in theory. It primarily gives you exercises to do and a little bit of background information on it. I'm going to supplement that background information with some more things I picked up here and there, and then this week the remainder of your assignment is your take-home exam, and whatever else is on the syllabus might be an OLM or something, I'm not sure. I have some additional information on setting up your accounts to use ArcGIS Pro, and so you should check your inbox to make sure and see if you have an ArcGIS Online account. I know several of you do, and so I'm going to check and see if you have them. If you do, use your existing ArcGIS Online account. If you don't, you'll use the one that I'm going to send you an invite for. And everyone will get an EVA code which will allow you to download the ArcGIS Pro software and some instructions relative to all this. Instructions will come in a day or so. And this is, I'm recording this on Thursday evening, so by Friday or Saturday you should have the EVA code which will allow you to have access to download the ArcGIS Pro software, and then the instructions to help with any problems. If you get stuck, don't fret. We can talk about it in class next week and get you squared away. But otherwise, we're going to kind of get started here and move right along. Okay, so Chapter 8 talks about spatial and temporal patterns, and we're going to cover the big things, like what are spatial and temporal patterns, what do they mean, how do we represent them, what can we learn from them, and why do they matter. So let's take a quick look at spatial patterns. What are they? Well, whether we're looking at spatial or spatial and temporal patterns, everything for the most part happens in space and it happens over time. So when you think about phenomena or things that we observe or measure in the real world, there's a location and a time when whatever it is that we're looking at happened. And we're talking about patterns in that. Patterns are non-normal or non-random distributions of data that indicate some uniqueness in their existence aside from chance. In other words, there's something there going on that's causing that data to not just behave as one would randomly expect it to behave. Now, in terms of these patterns, particularly spatial patterns, they can be clustered, they can be dispersed, or they can actually lack a pattern and be random in nature, in which case it's really not a pattern. But again, all these things tell us something about the data. So spatial patterns, what do they mean? Patterns could be an indication of a lot of things. For one thing, they could be a correlation with another variable. When you see certain clusters or certain patterns within data, maybe they're dispersed, maybe they're clustered. It could be that there is another variable, another environmental variable, if you will, that whatever the phenomena that you're measured or interested in is strongly correlated with. Think of it as things like more succulent vegetation only being found in spatial locations where there's available soil moisture. And so you look at this pattern and you wonder what creates the wonderful pattern of these succulent herbs. Turns out it's the places where there is sufficient groundwater near the surface. We can also make some assumptions that sometimes are correct and sometimes are not. We can look for causation or causality between variables. The ground is wet, therefore the water table is near the surface. things like that. There's also this issue of collinearity. We may be looking at patterns and think we're seeing a pattern in, for example, some sort of succulent vegetation, when what we're really seeing is a pattern that follows the underlying geophysical properties of the earth that create the conditions where these plants can exist. And that really only by looking at patterns within that area can we determine whether it's truly a spatial pattern in the vegetation, or is it just a pattern that is collinear with soil properties. Clusters are groups or occurrences where the density is in excess of what one would normally be expected by chance. In other words, if you know how many things occurred, and you know the general area in which they occurred, then you should be able to calculate out a good estimate of how many things should occur per unit area. And when there is a great violation in the math of that number, and you see much more per unit area than you would expect, then that means there are other locations where there is much less per unit area than what you would expect, and that is the indication of a cluster. More things are here than what we would expect randomly, and that is typically some location where activity is occurring, where something is going on. It's the place that interests us. It is the cluster within the data. Some data, of course, is dispersed. Dispersed is the opposite of clusters. Data is seemingly deliberately apart from each other. I think in class one night we talked a little bit about this, how in California, if you look at the habitat area or the territories of individual mountain lions, you will see that they tend to not overlap because they are solitary creatures, and the only time they come together are for mating purposes and while they're rearing their young, and then once they reach a certain age, mama cat kicks them out and they have to go carve out a new piece of territory for themselves. And so mountain lion populations, for example, tend to be dispersed, as in the territories where they roam are deliberately positioned so as to not encounter other mountain lions. And again, this is a type of a pattern. It's not really a cluster, but it's not random either. Other things we come across are value clusters. These would be things like hotspots. These are groups with higher values across a section or region of your data. And cold spots, which are the opposite. These are lower than expected values across a section or region of your data. In other words, it's not so much about the spatial configuration of the data points as it is all the points that are near one another have, for example, statistically significantly higher or statistically significantly lower values than what we would expect. And so even if the spatial configuration of the data points would lend one not to assume it is a cluster, it could actually be a cluster in terms of the values. So how do we represent these spatial patterns? Turns out bunches of ways. There are several types of maps and several types of statistics you can use to visually create representations of patterns within data. And if we think about GIS at its basic level, that's what we do. We take complicated information and create knowledge. And how do you create knowledge? You break down the complex into the simple and understandable. You take a data set that experiences some sort of phenomena that, looking at the data itself, is difficult to understand, to comprehend, and to visualize. You place it in the context of a map. Instead of looking at the raw data, you map out things like kernel densities and stuff like that, or hotspots, and you then show in a visual representation the phenomena or the particular aspects of the phenomena that are of interest. In this case, where are the high values? Where are the clusters? Those sorts of things. And we can do this with a lot of different statistical techniques, and we'll hear a little bit more about those as we move along. So what can we learn from them, and why do they matter? Well, clusters, outliers, these sorts of things, this is where the interesting things are happening. Why is the value higher? Why is the value lower? Why is this one data point separate from all the rest? Why are the data points so carefully positioned away from one another? Why are they clustered together in groups and bunches? These are all very important things because they speak to underlying factors, what's going on outside of our data set that could be influencing our data set. It allows us to do things like spot outliers and even errors, things that don't make sense, things that maybe are just simple typos or elements of the data collection process that were fouled in some fashion. We can learn a lot from these anomalies, not just from the normal data, but from the abnormal. It reminds me of the old Mel Brooks movie Frankenstein, when Igor goes out to get the brain for the monster, and he asks him who the brain belonged to, and he said Abby, and he said Abby who, and he said Abby Normal. Well, it's, with our data, it's the same kind of construct. Just because it doesn't fit the mold doesn't mean that it's not useful. In fact, it is often the data that is abnormal that helps us to understand the underlying relationships that control the phenomena at large. Temporal patterns are a little bit different. What are they? What do they mean? How do we represent them? What can we learn from them, and why do they matter? Well, when we talk about temporal patterns, we're really talking about changes over time. How things evolve, if you will, in terms of a phenomenon. We can look at rates of change. We can look at windows of change. So if we look at rates of change, how quickly is something changing? Let's think of glaciers, for example. We have glaciers. We measure where a glacier is. We come back. We measure it again. We come back. We measure it again. Over a period of time, we document where the edge of the glacier exists. Not only can we see how it's changing and how much it has grown or shrunk, we can also look at that rate per unit time, and from that construct models that will tell us when and if and how likely it is that the glacier will completely disappear or not. We can also look at these windows of change. Maybe we know that there's a particular phenomena of interest and we want to know what's going on during that period. Think of complex vegetative communities, and you want to know what was the impact of a particular event, say a flash fire or a big downpour or a minor drought. You could look at those individual windows and see how that time period affected the patterns of any number of types of data. What does it mean? Patterns, like I said before, can be an indication of many things. And temporal patterns, it often can be an issue of an environmental change. You could be looking at something as simple as seasons. We could be looking at changing boundaries. Think of the great browning edge that starts in the far southern part of the African continent, and as the season changes and the rainy season goes to the dry season, the line of green vegetation migrates northward, and it's followed by many things. Temporal patterns of the seasonal migration of animals is really in response to that seasonal change of where the growing vegetation is. So not only can we see that, we can also see the environment changing. We can see how the rainy season versus the dry season comes into play. We can see the changing boundary for where the herds exist and move. We can look at boundaries of political landscapes. How has the conflict in the former Baltic portions of the Soviet Union changed in relative to borders and that sort of stuff? Anything like that could be examined. Change itself is important. Change is not it's anything but constant, in that it's constant in that it's always occurring, but it's not constant in its state. Change can be a lot of different things. It can be a sudden lurch forward all at once, sudden rapid change. Think of, for example, something like, say an asteroid or a meteor hitting the Yucatan Peninsula, stirring up enough dust in the upper atmosphere to generate a winter that lasted for 3 or 4 years, killing the majority of the vegetation over the greater part of the earth, killing off the primary large herbivore species and the primary large carnivorous species that fed off of them, only leaving behind the smaller animals who could survive over that harsher period. That would be a very good example of a sudden and rapid change. Other things happen that are more steady. We can also look at the rates of change. We talked about glaciers earlier. That would be a good one. Basic movement of Earth. Mass movements of material along downhill slopes on mountains is not all rapid landslides in rainy seasons. A lot of time there's something that more closely would resemble a slow creep, where slowly over time the side of the mountain just slides away. If you've ever baked a cake and you put frosting on before the cake is cooled completely, the warmth of the cake can cause the fats in the frosting to liquefy, and the frosting will start to sag and slowly run off of the side of the cake. These are the sort of things that can be somewhere between slow or sudden. But we can look at those rates. We can also look for steady change and changes in boundaries as well, just like we've seen in the patterns. There's lots of different kinds of change. So how we represent them, again, lots of different types of maps, lots of different types of statistics. But they allow us to see some of these things. We can also see where the interesting things are happening, what are some of the underlying factors, what are some outliers or errors, and often, like with the other data, we can learn more from the anomalies than we can from the normal data a lot of times. So what are some of the useful mapping techniques that they cover in this chapter? Well, there are 4 primary things that they looked at, and these are basic geovisualization tools for spatial data. And the first one is kernel density maps. The second one is hotspot analysis. The third is 3D visualizations, and the last is animated data. And these are all ever increasingly more complicated means of displaying or learning from or interrogating or generating knowledge from data. So let's talk a little bit about kernel density maps. Kernel density calculates the density of features in a neighborhood around those features. That's what it says. What does that mean? Okay, you identify an area, around that, and you calculate or count how many of the other thing is occurring inside that area. And we can do this for points or for lines. Its possible uses would include finding like densities of houses, crime reports, in other words, how many crimes happen per area, or roads or utility lines influencing a town, or wildlife habitat. You could look at the density of roads or power lines that move through big-eared bat habitat or something like that. Tons of ways you can use it. Kernel density calculates the density of point features around each output raster cell. And so it starts out whether you have points or lines as your inputs. Your output is a continuous surface or raster, and for every cell it calculates this density function based on this area that you're assigning. Conceptually, it's basically a smoothly curved surface that is fitted over each point. The surface value is highest at the center location, and it diminishes with increasing distance from the point, reaching 0 at some search radius that you designate. Think of it as sort of a nearest neighbor kind of analysis, where the value is highest right where the point is, declining as you move further away. Now, kernel densities can also calculate the density of linear features. It works pretty much the same way, except instead of around dots or points, you're doing it around curved lines or straight lines. With the idea being the closer to a value, the higher, the further away, the lower. So when you do this, what does it look like? Well, a kernel density would literally take points like we see here on the map on the left as your inputs, and it would then generate a raster grid across that area, and then for every cell in the grid it would define a search radius, and for that radius it would identify the number or count of inputs within it. And it would do that for every raster cell, and then basically use a color ramp, if you will, to go from the values where the cells had none to the whichever one had the highest, and then apply that so that you could intuitively look at the map and see the areas that were darker as the areas where more of the input data occurred, or in other words, where the density or the occurrence of the phenomena in question was occurring at a rate that was significantly higher than what one would expect if the data was just randomly distributed across the entire surface. Now, the thing about the kernel density is it just looks at the counts. To really get into this, you need to look at it from a statistical side. In that case, we're going to look at something here called optimized hotspot analysis, and then just regular hotspot analysis. But we're not going to go too far into detail here in the slides. There are exercises in the book that you will do either this week or next week. You can go ahead and get started on them if you want. If not, they'll be there to be assigned next week. Alright, so basically, given incident points or weighted features, so points or polygons, it creates a map of statistically significant hot or cold spots, and it uses the Geddes or GI star statistic, which is a fancy way of measuring spatial autocorrelation. It evaluates the characteristics of the inputs and produces an optimal result. So with an optimized hotspot analysis, it doesn't rely on you to put the specific inputs in that you would do in a typical hotspot analysis. It does some iterative work to go through and identify, hey, this is where this variable should be. So the tool identifies all these statistically significant spatial clusters of high values, in other words hotspots, and these statistically significant spatial clusters of low values, i.e. cold spots, and it automatically aggregates the incident data, identifies an appropriate scale, corrects for both multiple testing and spatial dependence. Now these are important. Multiple testing and spatial dependence have an impact on the statistical validity of the assessment of probability. As you do multiple tests, it becomes harder and harder to not get a false positive or a false negative, and so the errors tend to add up. And so the p-value that you need to make sure that you have the significance that you want has to get increasingly smaller. Now, spatial dependence violates most of the primary assumptions of independence that we associate with most statistical tests, and so you have to take that into consideration when you're doing a lot of these tests. And so some of these tools will take that into consideration. Basically, the tool then interrogates your data in order to determine the settings that will produce the optimum results. However, after you've done this, and if you want full control over the settings, just drop off the optimized part and just run the hotspot analysis. This creates a new output feature class with z-scores and p-values and confidence levels for each feature in the input feature class. So the field that they're talking about there, the GI bin, it identifies statistically significant hot and cold spots, and that's corrected for multiple testing and spatial dependence using the false discovery rate correction method. That only means something if you're a really big stats nerd, or you had a bunch of stats classes, or if you have a couple copies of a stats book lying around that you're using to level up a pool table or something. This would be a good time to get one out and read about it if you're interested. But basically, it corrects this. Now, the z-scores and p-values that you see with something like this, they don't reflect any of the FDR correction. They're raw values. And again, your z-score just simply shows you whether you're above or below your mean and by how much. And then based on how far above or below the mean, it assigns an associated p-value, in other words, a probability that that occurrence was random. Next, we're going to talk a little bit about space-time cubes. They are one of those things that seem really, really cool and really, really complicated, and they are a little bit of both. Basically, it summarizes a set of points into this net CDF data structure. Okay, by aggregating them into space-time bins. Within each bin, the points are counted. For all bin locations, the trends or counts over time are evaluated. The trend for bin values across time at each location is measured, and it uses this Mann-Kendall statistic is what it's based off of. The output from this tool is a representation of your input points. You may visualize the cube point count in either 2D or 3D, and additional messages summarizing the space-time cube dimensions and contents are written to the results window, and so you basically can go in and click and it'll tell you a lot more about it. So a space-time cube basically looks like this, and so the moment you look at this, you realize pretty quickly that we're talking about an XYZ, a three-dimensional space of a cube in which the cube is basically a 3D raster. I'll throw a term out here you've probably never heard. It's a voxel, a volumetric pixel is another term that's sometimes used for these sorts of things. And basically it works kind of like this. Spatially, X and Y are the locations where the bin or the box is occurring, and what was previously your Z variable is now time. And so each bin is a spatial location and a moment or a period in time. And so as you go back in time, you literally just go down through the stack. And so the best way for me to explain this is if you took a series of aerial photos at the exact same location at the exact same time every day, and you stacked them up, or if you took them randomly throughout the day at this exact same location, and every, say, 4 hours you grouped them together. So if you start at the bottom of the stack here, you would have from midnight to 4 a.m., from 4 to 8, from 8 to 12, from 12 to 4, and from 4 to 8 o'clock at night. And so each cube, if you will, within the cube would be a 4-hour window covering a specific XY area. And all the images that you collected within that period, whether it's 1 or 20 or 500, would be in there, and it would average those numbers together and give you a value for whatever the parameter is you're looking at. And that is essentially how one of these things work, as near as I can understand. So exploring 3D data, or data in 3D, is really pretty good, pretty important, and pretty useful. When you look at things in 3D, you can look at it in two ways. You can look at it in a local view or a global view. In a local view, it basically takes the projection that you have assigned to the data, creates a 3D model at the scale that you're looking at the local things, and you can go on from there. Now when you look at global view, it literally takes your data and reprojects it on the fly into WGS84. Might even be in Web Mercator, I can't remember. Basically it reprojects it onto a globe-sized view. The detailed modifications of how you view it and a lot of the stylistically things that you can change are listed in the text. You're going to go through them. It can be pretty simple as to do. I mean, literally, if the information that you need is in place, you can literally just click a button in ArcGIS Pro and it goes from 2D to 3D. But it all has to be ready to do this, and so at times, while it may be as simple as a click, a lot of times it's a lot harder. Now, there's a lot of good resources out there to see what you can do in Pro in terms of 3D modeling. I've put a link in here to a YouTube video. What I would like for you guys to do is watch this. It's about an hour-long video. Apologize for that, but the presenter is going to walk through a lot of 3D stuff in ArcGIS Pro, and I think it'll be a good learning opportunity for you guys to see some of the 3D visualization stuff that you can actually do. The last thing we're going to talk about is animating your data. Now you might think, well, does that mean we're going to convert it into cartoons, or we're going to make it, more like Marvel cartoons, or more like DC comic cartoons, or more like Warner Brothers, like the Animaniacs, or more like Disney, like Mickey Mouse or Donald Duck? No, we're talking about creating a multi-dimensional, doesn't mean 3D, but it could be, construct where you can literally change time is the easiest way to think about it, and see how things would evolve or devolve or change over time. So you can construct, for example, a 3D visualization like that cube or something. You can add something called a time slider. And so with the time slider, basically, as you move the slider, it recalls the information from the relative time relative to the position of the slider, from the oldest to the newest, or the newest to the oldest, depending on the direction that you're sliding it. And you can literally see change over time simply by sliding a little bar. You can also add range sliders, which they say are really used to filter data, but I prefer to think of it as animating by variable. I'll give you an example. You just did those hotspot analysis. You've got this really cool map that's got these integrated rings, if you will, of probability around these data points of this is a high probability, like 0.05 out there, or 0.1, or whatever the values are. And basically, by sliding a variable slider or a range slider on that input layer, you can make it show all the value or some of the values. And so imagine sliding it so that it originally would show you all the intrinsic circles of probability, and as you move the range slider from left to right, it makes the less probable or the lower probable outcomes disappear, and so you go from having maybe 10 rings on the color ramp out from the points where you're really comfortable with, down to 8, down to 7, down to 6, to 5, and as you continue to move that slider across, it shows fewer and fewer volume of the data, and focuses in on, in this case, moving towards the data with a higher probability. So all these are great ways to geovisualize complex multidimensional data, which is really what this is about. GIS is as much a learning and problem-solving tool as just about anything else in the world, but the big difference is it's also a really great teaching tool. It's not always just enough for you to be able to understand the data. What really matters a lot of times in a lot of positions in GIS is, can you take the data once you understand it, once you make sense of it, once you learn from it, once you generate knowledge from it, can you take that data, that information, that knowledge, and use the GIS environment, the GIS tool, the GIS skills to teach that new knowledge to someone else, so that they can understand what you've learned without going through the painstaking process of all the homework that I assigned that allowed you to learn how to do it.